Okay, so hello, welcome to the support vector machines lecture. So the support vector machines in this basic form are linear classifiers. And if you remember, the last lecture was all about linear classifiers, about their advantages, their good generalization capability, and the ability to solve some standard statistical problems, like this two Gaussian in arbitrary dimension with the same covariance matrix, independent binary features, and so on. And if you remember, we one more nice property of the linear classifier was that we were able to produce a very simple algorithm, or we could, which was a perceptron algorithm, which finds a separating hyperplane line in 2D, plane in 3D, and hyperplane in higher D, that if the data is separable, in a finite step, we'll find a separator which makes no mistakes. So here we just like go back to the notion that the linear classifier is, well, we call it a linear classifier despite the fact that the function is affine because of the B, but we know that we can incorporate the B in the W with a measurement, fake measurement 1 in X. So we have this normal vector to the separating plane, and to make a decision, we do a scalar product between W and X, which is the same as projecting X onto the normal vector, and then we shift the plane in some direction by B, and the sign will be the classification, which means we are talking about plus minus 1. We can also write it like if the projection plus B is greater than 0, one class smaller than 0, the other class. And maybe we can say something before I start switching to other slides. Do you remember what were the disadvantages of perceptron? So SVM, support vector machines, is a classifier which solves perhaps all of the weak points of the perceptron algorithm. And there should be 2 or 3 that you could remember.
We require the data to be linearly separable.
Exactly. That was one weak point. So if the data were not linearly separable, we had some solution. We went for this gradient approach where we replaced the number of errors with the distance, and then the gradient approach could work, but that was one big problem. So if data was not linearly separable, we had to do something special. One more problem at least.
We have only 2 classes, like plus and minus, so we can't have more classes.
Yes, good point. So to generalize, perceptron can be generalized to more classes, but it does cost, in some sense, we have to lift to higher dimensional space through some special construction called Kessler's construction, but that is actually one of the problems that the SVM cannot deal with differently. So fine, good to Anastasia that you brought that up, but here SVM doesn't help. One more thing, which could be easily seen even from this image. So perceptron stopped with a separating hyperplane, which did not make a mistake. But one can easily imagine many hyperplanes which are not equally good. So if I switch to the camera, then if we have 2 classes which look like, perhaps the data look like this, then a perceptron would happily finish with a decision boundary like this, whereas we somehow feel, and in a minute, that a classifier like that with this fat margin here is much more suitable than the one that just barely touches some of those points, because if there was a noise around here, it would immediately not be so. So, I just realized that I forgot to connect the speaker, so it probably means that you cannot hear me well when I'm drawing. I'll try to fix this in a second. maybe you'll hear some weird sounds. I'm connecting this monitor. Okay, so now my default speaker has changed, but also the microphone. So if you don't hear me, say something. But now you could hear me even when I'm writing. So can you hear me well?
Yeah.
Okay, good. So that's fine. That's good. Fine. Okay, so let's go. So the SVM is actually a maximum margin linear classifier. So look at the two pictures on the slide, and the margin of a classifier is it's the distance. Well, actually, the sum of distances to the nearest example of one of the classes and the other class. Now, it's easy to see that these will be the same. So the margin is 2 times d of x, where dx is the distance to the nearest example from the two classes. And so dx, we denote dx the distance of a point from a training set to the boundary, to the decision boundary. Let's assume that the classifier classifies all data correctly, and then the margin is 2 times the minimum distance to the nearest point. And last week we talked about the concept of Abnik-Cherveningi's dimension, which somehow gives us some sort of probabilistic guarantee that the error on the training set, which we easily measure, and the error on test data, or actually the risk, which would be the error on the test data, which limit of the error on the test data if we do it for an infinite time. The bound has this risk part, which is a function of h. And we learned that h was more for linear classifiers, but we can show that there is a similar result for something with a fat margin. So we talked about that if we have a fat margin, then if the data lives in a sphere of radius r, we can show that it behaves as if if it had h, smaller than r over m squared. So what does this mean? If we are able to maximize the margin, R is a fixed thing. It's a sphere in which all the data lies. So that's a fixed thing, R. Now we cannot do anything about that. So if we find a maximum margin through H, we'll have a good upper bound on the real risk, and a good strategy to train a classifier is to try to push this to 0 and try to push H as small as possible by maximizing M. And this is exactly what SVM we're trying to do, and it's called structural risk minimization. Through M, minimize H, minimize this difference between the test and training error, and at the same time, push for small training error. That's the principle, and now we have to just formalize it and solve it. Okay, so we had this quantity dx, or distance, from the separating plane. Maybe we can put here w as well and y. And the y is plus minus 1, so this is just a sine function. So the top, so if you should know, but maybe you don't, if you have a unit vector u and a vector x, then the dot product of u times x, the size of it, is equal to the projection on the direction u. You can look at this like, this is 1, you have x size of x times cosine alpha, where the alpha is here. So this is the size of the projection. W, vector W divided by W norm, this is almost a question from a test in algebra, is a unit vector. Any vector written in this form, take a vector and divide it by its norm, will have this is a unit norm vector. So if we write Wx divided by W here, this is the projection, and B is just saying, okay, our 0 will not be at point B, but at minus B. So if we want to have the separating plane here, this will be minus B divided, actually, the way we write it here, it will have to be divided by W. Yeah? So the B is the offset. So project and then do the offset. So this is the distance from a separating plane. By the way, most of you know this from secondary school, where there was this ax plus by plus c. This is what teachers want at the secondary school. They want this formula, like distance of x from a plane. And we know that this a and b is the normal vector direction, which we call here w. You see that this is ad. We see that this is actually norm of w. The c is the offset. And now the absolute value was giving the distance in terms of a positive number. And here we see, okay, we are keeping the distance signed. So this y that says, okay, for one class, we see the positive distance in that direction and negative in that one. And the y, and for the other class, it's like for y1, it will be this way. And for y minus 1, it just sort of changes the sign. And we are keeping the distance as signed distance. So on the right side, it will be positive, and then on the negative it will be negative. So you see the formula C here, or we want, for the optimization task we want to solve, is find the W and B, which are the parameters of the classifier. Find it so that we maximize the margin. So this is a maximization over W and B, which are the parameters we control. For once, what do we maximize? The distance of the nearest point from the training set, subject to all points are classified correctly. So the distance is positive when we swap the sign of the class. So one class on one side and on the other side. This is plus minus 1. So now we have formulated the optimization task. Now, what happens next? We have to a little bit work on the formulation to simplify it. But let's check. At this point, I assume that the formulation C is clear to everyone. Say yes in the chat or something like that. So
I would like to ask,
yeah,
why there is a number 2 in the optimization task, where we minimize two distances.
Because once we take a derivative of a quadratic function, it will no, it doesn't matter. It's like, of course it doesn't matter. This is equivalent if the 2 is not there. This is just for convenience, just to make sure that what is optimized is the margin. We can of course optimize half of the margin, so it doesn't make any difference. Yeah.
Okay.
Fine. So now one thing we have to sort out, and this is something that most people find difficult to sort of fully digest, but maybe if you don't digest it here, you can think about it at home. So first observation, the formulation, like the definition of a hyperplane as we gave it with W and B is not unique. If we multiply W and B by any constant, non-zero constant, we'll get exactly the same decision boundary. That's explained in formula 3. And the distance is everything is the same. Yeah, if you multiply by your vector nb by a scalar factor, no change. So now this is inconvenient because obviously we have 1 degree of freedom that is redundant, and that might complicate things. So the thing which we can do, we'll say, okay, we want constraints to be positive, but that's actually the same thing that there exists, same thing as saying there exists an epsilon greater than 0 that all our points satisfy the formula that I'm highlighting. So if for all points, the inequality class plus minus 1 times projection plus b is greater than 0 is the same thing as saying there exists an epsilon. Let's require this epsilon to be equal to 1. So we'll say, okay, maximize the margin subject to projection is greater than 1. Now, that's allowing us, like, the 1 is not so important because if we are greater than any epsilon, we can make w and b smaller. So if you imagine, now look at this right side. If it's not large enough, it's just, for instance, bigger than 0.5. I multiply w and b by 2 and I satisfy this. If this thing is only 0.01, I multiply by 100 and I satisfy this equation. So by rescaling w and b, I can satisfy this inequality, and it's exactly the same thing as 0 on the right side, because I can rescale. That was the redundancy. And I fix this redundancy in the scaling factor by fixing this number 1. So now I can change the formulation to maximize the margin, which now becomes, okay, not the margin. The margin will be 1. We will not maximize the margin. We'll say, okay, we keep the margin, but we'll try to achieve this constraint with minimal w. Yeah, because now that we fix the scale with the margin will be plus minus 1, so the margin will be 2, and we require the constraint greater than 1. We want to achieve this with as large 2 over w, so with very, very small w as possible. So we say we can satisfy this by making w and b big, but let's make w big and b just b. Now we'll say, okay, so the classifier is good if the w is actually small and still the inequality holds. Yeah. So another point, you can look at this another way. If you think about rescaling wx by some scaling factor alpha and doing alpha here, we can also say, well, if we have a margin and we try to make rescale the points so that the margin is still valid, but the points are in a smaller, tighter circle. So there's this scale ambiguity, and here we should have shown, let's go from here, saying first, bigger than 0 is the same as epsilon, because if it's bigger than 0, we can select every epsilon because we could rescale w. So let's fix this epsilon to 1. This fixes this margin, and we'll try to achieve the margin we will achieve this constraint with a margin of 2 with as small as W because the margin is 2 over W. So now we get to the final formulation of SVM. So maximizing 2 over size of W here is the same thing as minimizing the vector W. I actually said this already, subject to everything outside of a strip of size 1. So that's the final formulation. So we started by saying, okay, we wanted a classifier that would be as thick as possible because of this n role in the difference between test and training data. We wanted to have everything, we wanted the training error 0. So the bottom thing has training error 0, and subject to training error 0, we maximize W, we minimize W, which is maximizing the margin. And in a sense, we could finish here. So this is a quadratic function of the W, and this is a constraint. So this is a constraint optimization problem with a quadratic cost function. And in mathematics, this is classified as a quadratic programming problem, and it's solvable by standard libraries for optimization, or maybe algebraic solution solvers and so on. So maybe one can think about it. This is solvable, and it's actually solvable to a global minimum because it's a convex problem. So we have discovered that we can solve, and this is now magic, that we can solve the problem of minimizing error on the empirical error and also getting the margin with the quadratic programming approach, which is globally solvable. Things look extremely good. So in the slides, you can look at some example in 1D, how this looks like, what the solution would be. But now we'll spend some time on transforming the problem into the dual formulation so that we can see some nice properties and the solution of how we achieve the solution. Yeah, so someone who doesn't want to know much more, let's say someone who wants to use SVM, he goes, finds a library. We used in MATLAB, it was called QP. In Python, I'm sure there will be something similar named, and runs it, and he's fine. So let's have a look at to get some insight. So we'll actually do something that you probably know with Lagrange. We'll use a method which is often called the method of Lagrangian multipliers, but we'll spend a little bit of time on this. So we say, okay, here we have a constraint optimization problem 9, and let's make it into a different problem without constraints, with some extra variables. And we could see that if we add to our cost function a term which looks like this, sum of x, y, w, and b, where f has this property. It's equal to infinity if the constraint is not satisfied, else it's equal to 0. So adding such a function to our w just means, well, if you minimize that new function, then if your constraint is not satisfied, you'll get infinity, so that will not be your solution if some feasible solution exists. And if you find a place where all the constraints are satisfied, they will add 0. So you are actually minimizing what we want to minimize in the first place. So this is a way how to transform a constraint optimization problem into an unconstrained one using, and then maybe we can look at, so now we introduce, say, auxiliary variables, which are non-negative, and say, well, the problem which we see in 12 that I just explained is the same as the problem of 13, where this is the constraint, and we say, okay, we'll add these variables alpha, which are non-negative, and what we want to do is minimize over w B and maximize over positive alphas. So now if you look at this, if the constraint in the original setting was satisfied, then the maximum here we can achieve is 0, and for alpha 0, if it was not achieved, then we have the well, this would lead to a maximum value, so we can't do that. We'll have to find a solution where this doesn't happen. And if this constraint is exactly satisfied, so it's exactly satisfied, then we can achieve 0 for some alpha which is greater than 0. So because we maximize, the alpha will be non-zero. Now, after like reordering this min-max, we get to this Lagrangian term, which says, well, what the original can be transformed into the minimization of the norm, quadratic norm of W, that was the original thing, minus some constraints with these Lagrangian multipliers and the conditions. So this is something that you probably know from optimization. If not, you will have encountered soon. But in the end, we wanted to transform our problem to this form 19. And now we can look at, so let's say we have this criterion constraints in the form of Lagrangian multiplier times condition. And we want to find the minimum with respect to W and B. And let's have a look. So we'll take the derivative with respect to W and B for fixed A, alpha. Now, so where does W show up? So this is a derivative with respect to vector. This is like a vector of the derivatives for individual components. So if you take this norm squared, this is nothing but a sum of Wi, and 1/2 is here just exactly to cancel out when we take the derivative. So if we take a derivative with respect to Wi, the only Wi that will stay. What will happen? We'll have W left. So then, and in this part, when we take the derivative with respect to some element of W, it will be alpha I, yi, and xi. This part will disappear, and then we can also organize it to a vector. So the result is the optimal solution W has to satisfy this constraint that it will be some combination of the input vectors xi, some, those which have alpha I non-zero, and the vectors will be multiplied by plus minus 1 depending on the class. By the way, if you remember perceptron algorithm, it also came up with a solution which was a linear combination of some of the inputs, like the alpha was not there, but some input vectors, those incorrectly classified, were added to the solution with this sign. Now let's take a derivative with respect to B, and the condition is alpha I, yi equals 0. So fine. Let's put this back into formula 20. So we start. So this is just a copy. Now we can insert for, okay, first we slightly rearrange these things, distributing the alpha. Yeah, so some alpha y x I w, this is the first part here, and this is the formula which involves B. So now we can take B out of the sum, and that means that this term will be 0. The sum of alpha I stays here, And if we substitute for the W from alpha I, yi, xi, we'll get alpha I, alpha j times xi, xy, xi, xj. So that's substituting from 21 for W. So fine. What we achieved is that we got the formula 23. Now we have potentially n. We have n alpha i's, where n is the number of training data, but the support vector number will be very small. Like in the general case, in the class, it will be and d plus 1, where d is the dimension of the space. So we know the alphas will be non-zero only for the support vectors, so we can calculate in the end the W will be a linear combination of a very small number of input points, and the B will be obtained by substituting one of the support vectors into this equation, and we'll get the B. Okay. Now an example. So here we have 3 points. If we look at this formulation, sum of alpha i's, so the things which we know is xi, xj, and we know yi, yj. This is plus minus 1. So in our case, the points are like after the in 2D, we have 1, 2, 0, 1, and for their class 0, minus 1. We'll calculate the matrix, and it will be, it's a matrix which is symmetric, which has to be, because if you look at it, dot product x2 dot xj, xi, xj is the same as xj, xi. And we are trying to solve this, say, you see the quadratic function. Here, well, we can substitute for alpha 3 with alpha 1 and alpha 2. And the solution becomes like, the only thing we are looking for is these alpha 1, alpha 2, then alpha 3 will be computed later on here from alpha 1, alpha 2. And this is a quadratic function in 2D, and we can find a solution. And the feasible region here is, you see positive alphas, non-negative, sorry. So, and the global is outside of that feasible region. Okay, so, and the solution, we have 2 support vectors, which happen to be the point 0, 1 and 0, minus 1. They are a linear combination of the input points with the weights 1/2 and 1/2 and 0, and the offset happens to be 0 because it passes through the origin. Okay, so maybe one property that we notice that maybe in this example, that where did our information in the training set is in the form of some vector of observations, xi, and class a I. And I was up to n. We have n training points. Now, and the only thing we had to do with all the data points is to create an n times n matrix, which had the dot products. So I will put it like this, xi, xj. Now, what that means that the optimization problem doesn't care about the dimensionality of the data. So if x is from Rd, in the optimization problem, you won't see it, because once you compute the matrix, this is a matrix of real numbers. Yeah? So that's okay, maybe the method is quadratic in the inputs, in the number of input vectors. Okay, there are methods which can perhaps, and they are methods for very large n, the n square could be prohibited, but there could be methods which do not explicitly build this whole matrix. Yeah. So if you go for the straightforward solution and you create this whole, let's call it D, this data matrix D, it's quadratic in the input, in the size of the training set, which perhaps could be seen as one of the weakest points of the SVM optimization problem. Okay, so let's go back. So far, we solved one problem of the perceptron, which was the problem of selecting among, so what was the one problem of the perceptron was that it gave one classifier which was error-free, but now we can give the one with the biggest, largest margin. So we move. Now we go to this other second problem, which was, what do we do when we have a non-separable case? So now we know from computational theory that minimization of the, finding the classifier which minimizes the number of errors is not computationally feasible. So what we do here is we introduce slack variables psi, and we say, well, this solution, this problem doesn't exist. We cannot, there's no feasible solution satisfying this, so this constraint. So we allow some slack to be introduced, and it's the distance from the margin, edge of the margin, not from the separating hyperplane, from the margin, and we'll add the penalty to the minimization term. And now, and we'll relax this constraint 32 by saying, well, now we don't want to be greater than 1, which means on the right side of my margin of width 1 for some small w, but I'll allow some slack here. Now, this is always solvable because we can put here some large number if need be. Yeah, we say, well, okay, if this thing on the right is not large enough, add psi I of arbitrary value to make it sure. So if you put psi I close to infinity or something, anything bigger than the projection can be on the, you will satisfy. So, okay, fine. We have a new formulation, 2 weaknesses, we see that. So first of all, so now I'll draw this like a classifier. So this is the decision plane. So we're looking for a classifier which will try to find something separable. Maybe this will be crosses. But if there isn't, there's no separable one, but okay, I have to be very careful here. It says, okay, now I will allow incorrect data which are on the wrong side of my margin. So even this point here, which is classified correctly, is on the wrong side of this margin of width 1. Yeah. So also you will pay a penalty even for, so this point pays a penalty, yeah? And the penalty is proportional to the distance. So so if we look at it, if we move into this direction, the penalty you pay, loss, grows from 0 at the margin by distance, with the distance to the margin. By the way, unlike with the perceptron, this is upper bound of the number of errors, because the errors start here and it goes like 1 and 0. At this point, at the point of the decision boundary, the decision boundary is here. At the point of decision boundary, you pay 1, and that's where you switch. So it's always this loss which we introduce is an upper bound of the classification error. By the way, this loss, the loss, maybe I'll draw it here. 0 and okay, maybe I will do it this way. So this would be correctly classified, incorrect. So this would be right. Maybe this is the distance, the signed distance from the decision boundary. Yeah, so if I'm on the positive side, I'm correctly classified. This is incorrectly classified. This is the loss. So the blue loss is counting errors, and this is the point 1, because we have a margin of plus minus 1, and this is called a hinge loss. Maybe hinge is not such a commonly known English word. It's the thing that holds the door. Yeah. So if you have a door, it's hinged here. Yeah, hinge loss. Also, you will see that this is very close to something called ReLU in deep networks, which means rectified linear unit. So if you have a linear unit, this is it, and rectification in signal processing means clip whatever is negative, make it 0. So this is a very important loss function. Okay, so now we have an optimization problem which is always feasible. There will always exist a W and B which can solve this. And the price we paid is that we cannot fully justify. We are not optimizing what we would like to do, because if you remember in this formula, original one here, we would like to minimize that, but we are actually now not minimizing it. We are saying, okay, we have this C times sum of psi I, so we have this upper bound thing. So this is an upper bound, but not the number of errors. And unfortunately, we had to introduce a constant C, which we'll have to find somehow. But for that, we can solve non-separable case. And interestingly, the dual looks exactly the same, subject to alpha smaller to 0. It has to be positive and smaller than C. So again, if you have a quadratic solver, the solver will do the job for you. So we have solved. So the positive thing of what we are doing here is that we managed to solve the problem, which for non-separable case with the same machinery. Yeah. So again, you will not be writing a solver of a quadratic programming problem yourself, and it's pleasant to find out that the solver will deal with the separable case or non-separable case almost the same way as the separable. Okay, so now summary of the linear SVM. It finds a separating hyperplane. In some sense, the most important training points will become support vectors. They define the hyperplane because the hyperplane is a linear combination of support vectors. A quadratic optimization algorithm will identify the support vectors. These are those with non-zero Lagrangian multipliers. And the only way the input data, the measurements, appeared in the solution was as dot products. By the way, an interesting point which is not immediately obvious, if we have two classes like that, perhaps, then let's say the SVM finds this, and the support vectors will be these three vectors. If you inserted only these three, where your training set, this is your training set T. So if you only pass to the minimizer these 3 points, you will get the same solution. So lots of your data points are not needed. And it also means that the SVM sort of doesn't know it's actually technically not a statistical classifier, because it only cares about this points which define them. They have the minimum distance to the boundary. And if the distribution here looks like this or like that, it doesn't matter. Fine. So now we have to touch one more problem that we had with perceptron. So what if if the decision we want, the decision boundary, is not well approximated by a linear function, possibly something like that. There is no good linear function. So we already touched this one in last lecture, and what did we say? Well, for the first problem, red on the right, left, blue on the right, there is a linear classifier, which in 1D is the threshold function, or actually a thresholded linear function, signum of a yeah. Then, and for two, if we need two thresholds, like say, well, the blue class is somewhere in the interval between 0 and 1, and the rest is red, we could still solve this by mapping our only x1, the single number we had, into x1, x2, and in this two-dimensional space, where the data which originated in one-dimensional lie on a one-dimensional manifold, but if we treat them as two-dimensional, there exists a linear classifier with a fairly small margin here, by the way, that separates the two classes. So there is this trick of saying, well, directly I am solving a linear problem, but by lifting to a higher dimensional problem, I can transform the quadratic or other type of boundary into a linear problem in higher dimensional space. So let's have so that's an example. And I have like 3 examples here, and probably the best one to start with is the quadratic. So I'll start and then come back to this generalization, and I'll go here for quadratic. So what do you have to do to find the optimal, from some point of view, quadratic surface separating the crosses and the circles? Now, let's consider, so here we have 2 measurements, x1, x2, and you see the slide, but let's have a look at a general form of a quadratic function in 2 dimensions. So it's something like ax1 squared plus bx1 plus cx2 squared plus dx2 plus ex1 x2 plus f times 1 equals 0. Yeah, that would be a general form of a quadratic function. It's much more elegant to do this like a quadratic form with matrices, but let's leave it like that at the moment. So now, if we take x and y and produce a 6-dimensional vector, x1 square, x1, x2 square, x2, x1, x2, maybe I'll put commas here, and 1. And we can think about some new space, z1, z2, z3, up to z6. And if we look for these, for some weights, w1, w2, w3, up to w6, so any quadratic function in the original x1, x2 space will be expressible by a linear function in the 6-dimensional space. So we can find these, if we work and find the classifier in 6 dimensions, it will give us these weights, and we can solve the equations if we want to go back, and it will be, these will be the quadratic coefficients of the quadratic function in the original space. Now, so that's what is on the slide. The fact that you have the square root of 2 there doesn't make any difference. It's just like convenient. It's just a slightly different parameterization, nothing else. Now, just a question. I have to make sure. Do you see what you've seen things like x2 over probably you saw something like that. What is this formula? So how would you describe this formula?
It's like not circle, but ellipse.
Ellipse, yes, it's but maybe what type of ellipse? Can any ellipse be described by this formula?
It's not rotated. It's only
Okay, axis aligned is the word, yeah? Yeah. So this thing can, so okay, this is axis aligned ellipse centered at 0. Something like center x, center y, b square. This would be non-centered. So we have 1, 2, 3, 4 parameters. The rotation is actually here. And the 6th parameter is like it's this ambiguity that we have six numbers, but only 5 play a role, because if we multiply this vector W1 to W6 by a scaling factor, nothing happens. So the rotation is something that you don't really normally, most people will not be trained to do that, but you can do it like X, you can do it like maybe these are vectors plus, or maybe plus 1 equals 0 or something. So this matrix C here, maybe you can't see it, but this can be seen as a when the matrix C is diagonal, and ellipses are 1-to-1 to covariance made positive symmetric definite matrix, positive definite symmetric matrices. What I want to show that maybe you don't see, or for parabola, you saw something like this at school. So lots of things are 0 then, but this is the general form. It can be seen, it can be written in a matrix form, but the point is that we have a way of expressing circle in a linear, like all second order polynomials or quadrics using a linear form. Now this thing shows one fantastic thing called the kernel trick. And I will show it on this example and then come back. So you remember, what do we remember? That when we were solving SVM, the only thing that showed up was the xj, x, yj, yi. So this is something plus minus 1. And then we had a dot product. So let's calculate the dot product here between, so phi of x is this lifted vector. We took 2 measurements, we lifted into 6 numbers. We have 2 points, x and y. Let's do the dot product. So what do we get? 1 times 1 is 1, yeah, plus 2 times x1, y1, plus 2 times x2, y2. So now x is first point, y is the second point, and 1 refers to the coordinate, plus x1 squared, y1 squared, plus, and so on. You can check yourself very easily that you do not have to calculate this dot product in the 6-dimensional space here, but it's exactly the same number as 1 plus x1, y1 squared. Yeah? So if you take this dot product, what is this dot product? That will be 1 plus x1. So this would be just x1, y1 plus x2, y2. This is that thing. Plus 1, take the square of that. And when you make all these when you multiply it all out, you'll get exactly the same sum as if you first went to the six-dimensional space. So for these transform spaces, there exists a kernel function, that's this kxy here, that is exactly equal to first mapping to high dimensional space and then doing a dot product. But you can have a kernel function that is much simpler to calculate, and it's exactly equal. So let's come back to this box, the data matrix D here. If you prepare the data matrix and you run your quadratic optimization problem, what do you get? The maximum margin, max margin, linear classifier. What do you have to do with this data matrix to get a max margin classifier which is quadratic in the original space? You take this data matrix, and for every element, and I can imagine you can write this in MATLAB or parallel Python in 1 or 2 lines of code. You say, well, I take the original xi, xj, okay, there's this yi, yj, which is just this plus minus 1. And I'll just, well, that's, okay, we'll read that at the moment out. We'll add 1, and then we'll multiply. That's the only thing I have to do. And now the QP gives me a quadratic classifier. I would say this is a kernel magic trick. Yeah? So by just adding 1 to what you had and squaring and using exactly the same solver, the quadratic programming solver, you'll get a quadratic classifier. Now, okay, maybe this is a simple example just for the parabola. Same thing, this is a special case. Instead of, we can map x to xx squared. If we have 2 points, xi, xj, the dot product is ai squared plus xi squared xj squared. But we don't have to do this explicit mapping. It's enough to say, calculate x1, xj, and the kernel looks like this. So this is again, it's exactly the same formula, but the 2 is not here, yeah? We take the data matrix, this xi, xj is what we would have in the one-dimensional case, add 1. Okay, it's not the same. You say, well, add 1 and multiply it with the original value there. So very easy. The general formulation is this. There exists a huge class of functions which we can call kernels, and they have to have this property: they are symmetric, like dot product, and they are positive definite, so that can be used in SVM calculations for SVM. So we say, well, we'll say our data matrix will not be a matrix of xi, xj. Okay, like what I mean by this xi, xj, that here we have x1, x2, and so on, and here we have n, okay, xn, but maybe this one is x1, xn, dot product. We will not build a D like that. We'll build the D differently. We'll build it based on kernel xi, xj, and we can do that even if we did not know what the embedding of x that leads to this kernel is. So
I'm sorry, we cannot see the bottom of the paper. At least I can't.
Sorry.
Yeah.
I turned it like that. Good.
Yeah, thanks.
Yeah. So we could go 2 ways here. We could say, well, nothing is happening. We go x, map it to another space, and calculate fxi, phi xi, phi xj. That's one way. If we know this mapping for the polynomial we knew, But maybe we don't have to go this way. We can just say, and this will give us the data matrix D. The other way to go is to compute directly xi, xj using the kernel function. And for 2 examples, we show the kernel function. The interesting thing is that even such a generalization can be calculated exactly like before. We have this new data matrix, which is not full of dot products. It's full of this kernel dot products or kernel responses. And the solution is again a linear, the W is a linear combination of this response at xi, where xi is, it's not sum over all points, but only over the support vectors. And then when we are computing the decision function, and we calculate it as not as dot product with the W vector, but as a kernel response. So X is what we want to classify, xi is a support vector, kernel response, and this will, we check the sign of this function. Now, there is one problem that makes the kernel operation more difficult. So in a linear function, we had W, the optimal solution was some sort of, I'll be consistent with this, HI or HI, YI, XI, and the classifier, which is called here FX, was W star X, these are vectors, plus B, which is the same thing as sum HI, YI, XI, X plus B. Now, in the linear case, we'll do it always like this. Calculate W, get one vector. For decision, do a dot product of 2 vectors. So memory complexity of SVM is just remember this vector. Execution of the decision, do single scalar product. We could have done it the other way around, but it would be much slower, which is if you want to classify X, do the dot product with every support vector, and then sum it up with this Lagrange classifier plus minus 1. So this would involve, if we had S support vectors, this will involve S dot products. You know, you can do it, this is associative, so we can do either this first and then dot product with X, which is much faster, or dot products, nobody would do it the second way. But in the kernel SVM, we see that we have some HI, YI, kernel X, XI, plus B. So you have to compute the kernel function for all the S support vectors. And which means that also you'll have to store them. And every time you want to classify, you will have to go for this I over the set of support vectors. And we said it's going up to, yeah, so there are S support vectors. Now, if you have explicit mapping, like we talked about, we had this x1, x2 to this x1 squared, x2 squared, x1, x2, the product x1, x2, and 1. What we could do it explicitly, and then we could do this exactly in the 5-dimensional or 6-dimensional space, or we don't have to do that, and we go to kernel, and every time we classify, we'll have to use the kernel. So computation, like solving the solution of the problem uses the same machinery. You end up with the same characteristics of the result. You will have the Lagrange multipliers, which are non-zero for the support vectors. But if you do not have the explicit mapping, if you have the explicit mapping, so here phi of x could be a 5-dimensional vector, fine, your W is longer, no problem. But if you don't want to use this explicit mapping, you have to compute the kernel response for the input vector and all the support vectors. Now, here you have a choice, here you have a choice. But now another thing comes in. This is a very big strength of SVM. Look at this function on top. It's like for any pair of x, y, x, j, this is a positive function, and it's symmetric. You can use this, and it's a very popular kernel. So if you use this is called radial basis function. Radial because there's something which looks like this norm is like a distance norm, and it has a say spheres as isosurfaces. So what is happening? What is happening in this example is that, okay, I do my data matrix by taking, when I'm training, I take my xy and I calculate xi minus xj. This is a vector of dimension of the input space. The norm is a number, square it, and fill in these real numbers into the data matrix. So fine, then we do QP. What do we get out of the QP? The Lagrange multipliers, let's call them alpha or h here, whatever h, I, so we know which are non-zero. And then, okay, once it comes to evaluating the classifier, we will have to use, in this case, sum of hi class and kernel function, which is x minus this minus 1/2 x minus xi over 2 sigma squared. Now here there exists an embedding, but it's very high dimensional and non-linear mapping, and it could sometimes be infinite dimensional. So in this case, we have no other choice than to say, well, let's store the support vectors, and we'll have to find the classification with the kernel function. So this is the k, where xi is a support vector and x is what we want to classify. So for this type of functions, we have to do it this way, with the explicit storage of all SVMs, and then calculation of this response function. Okay, so there's like, if we look at SVM, people have experimented with many kernel functions, especially when SVM was on, let's say, the most popular machine learning tool. Practically these days, people use only 3 types. The Gaussian kernel, which sort of allows you to build the SVM with shapes like isocontours of mixture of Gaussian, polynomial with power p. So this is equivalent to mapping the input space to a p order polynomial. So what we went for second order polynomials, but we could go for third, fourth power. I think higher powers are not often used, or a linear kernel. You can have even a kernel like hyperbolic tangent, which is similar to a 2-layer dense neural network. So you can formulate it as a kernel function. And I think this is not very popular. So there's some example of, we played with some examples here, like if you have a dimensionality of a space and you have a lifting to a polynomial of degree 7 or 8, you can see the number of parameters that are in that space. Because when you go for this monomials, like the number of monomials is given by this combinatorial number, and it's not because the things repeat. So you see that it's very easy to go to very high dimensional spaces and then find linear classifiers in these dimensions. So one example, so here we have data which are actually separable, and we go for linear classifier. We have 3 support vectors. We are in 2 dimensions, and if one decides to go for a second order classifier, you end up with 5 support vectors, but you see that maybe it's not giving anything. It's quite smooth boundaries, and I would say the classifier is still fine. Interestingly, if you go for higher and higher dimensions, still the classifiers are fairly, it doesn't go into any mad, very wobbly decision boundaries. You see that it's quite stable, despite the fact that already the linear classifier had a good margin and was a good solution. There are, okay, there maybe, this is the last slide. There are examples on the web that you can find of SVMs that you can, like JavaScript things in your browser, you can click and play with it. Now, but let's spend this time that we still have on the summary of SVM properties. So positive and negative, and I think you should be able to do this. So what would you see as positive points and weak points of the SVM classifier? So please go ahead. Like this will remind you, remember what we learned, and also then maybe you can already now compare with the you can compare with the nearest neighbor, logistic regression, and that's the 2 that we've already talked about. Yeah. So please, some thoughts about what is a strong and weak point of SVM. So you should be able to come up with something.
Yeah, strong point. The last one that we discussed was that we can map nonlinear. Yeah.
Okay. So this is mainly against, for instance, logistic regression, the kernel trick. So efficient nonlinear classifier, like learnable. Yeah. But maybe this is the last thing. Let's start from the basics, and let's try also to find something negative.
A positive, we don't really need to know a lot about data.
Yeah, so maybe this can be transformed into fact that what are the parameters that one has to fiddle with. So you try the polynomial, which the linear is 1, 2, 3, 4. And usually this one of them will work rather well, plus this, what is called RBF, which was the Gaussian type kernel, e to minus x center 1/2 device squares to, okay, sigma square. So if you have, for a broad range of data, you can fit them with one, you can find a polynomial boundary of some order or RBF. And so not much fiddling, like especially if you think about neural nets, which architecture, which loss function, which nonlinearity, add this or that. But there are only 2 parameters. One was the C for the nonlinear case and the sigma here. So that can be usually found by cross-validation very fast, because you have only, like, in these cases, only 1 parameter, and in the RBF 2 parameters. So nothing to fiddle with, yeah, okay? We have global minimum, of our functional. The cost function, the loss function, is well justified because through the constraints we are heading towards empirical error to 0, and through this maximum margin we are pushing h down. Yeah. So this looks all fine, but try to find something negative or something even more other positive things. Lots of aspects that yeah.
I would say that it's bad for large data sets.
So okay. So for large data set, there was this O(n) square, which is a problem. And as usually in computer science and in machine learning, there are some maybe partially mitigating methods which can in the end, this is a computational problem, and there are methods which do not that have like complexities with O(n), let's say, space. And we have not talked about the algorithmic complexity. So if you want to deal with large problems, you need, let's say, special algorithms. So often you might have things like, okay, I assume these things are support vectors. R is everything. You can do like use active set methods. There are methods which can deal with this, but you need some clever algorithms to deal with that. Maybe what else? Okay, maybe
It's sensitive to noise. Can you tell this?
Yeah. Yes. So noise sensitivity is like so sensitivity to noise. Now we'll see next week. I think ADA boost, which is even worse, but probably to noise. Now I would put this as like plus minus. Yeah. So yes, it's not like if it's really far, then the psi I of that. So this will be, so if a point is really an outlier and it's on the wrong side of the decision boundary, you will pay this penalty for it. So it's linear in the distance. It's not exponential, as you will see something next week. So it's linear, but it's still a problem. Yeah. So it's more like a minus. I agree with that. That was a good point, Anastasia. Good point.
And also, as you've said at the beginning of the lecture, we can't solve this case with multiple classes very well.
Exactly. So I think already this, okay, so I'll write Anastasia. I'm not sure whether this is, I see Ostap, so I will put Ostapenko, like, let's, is it, yeah. Okay, so like the tennis player, I will remember that. And do you have a point? Because that's nice, what you said. So okay, so for class number bigger than 2, we have to do like, again, it's like I would say big minus and small plus. Again, it's solvable. The solvers, but for instance, not for k much bigger than 1. Yeah. So there, it like you can generalize the formulation to multiple classes. I think you will do that in the labs, but it sort of costs again. You get the solution means adds complexity somehow in various ways and maybe reduces the some of the guarantees that you have in terms of generalization. Yeah. So okay, so here we have on the plus side good generalization. Because we have this age. And so, by the way, like SVMs where the hit may be from around say 90 to 2000, SVM was like the top dog in machine learning because this is very impressive. Yeah, some more. Yeah, okay.
Oh, thank you.
Yeah. So I have to be careful here. So in the 90s, like in 86, people came up with neural networks, the classical ones, which were trained by backpropagation. And okay, that was like really first, like almost a revelation, because this was the first learnable classifier. You didn't have to write the algorithm. You could learn something, but you had the problem of overfitting, local minima, lots of things. And now SVM came, and they said, well, you don't have to fiddle with these parameters. We have only a couple of those things. We find the global minimum in the optimization. Why you don't have to repeat any steps and try different local searches and whatever. We have a very nice and justified loss. We have good generalization. What more do you want? Yeah, and maybe what you want is huge training sets, large number of classes. I think this sensitive to noise can be again somehow handled. There's one more thing which is probably for you. It would be too early to ask for this, but you can x's are real numbers, yeah. So maybe like in a decision tree, you can ask things like red throat or not, yeah. So it's because we also have this dot products and so on. All measurements have to have a formal, a numerical form. So. But we are now getting quite picky. Like maybe I'm saying all of this to see how many aspects you can think of. Okay, so especially for the linear, very fast because it does dot product, and memory, small memory requirement low. So okay, for the nonlinear. It can often be also fast, but then there is the dependence on the number of support vectors. So if the support vector number is not too high, it will still be very fast. So the execution is so fairly simple. So you see that lots of interesting properties. SVM is still widely used, and I think mainly for cases with small, like all of this is now suggesting you have data, the data set is like small training set, means that this is not, the efficiency is not a big deal and so on. So small problems in small data where you want simple, transparent, well-justified algorithm, that would be the domain of SVM. So questions?
And can you add previous lectures to the courseware?
Yes, with some, yes, perhaps, yes. I don't have like one recording